And yeah, it's a personal perspective. So as you probably have heard about encyclopedias before, and yeah, so I'll get to what I really mean by this in a minute here. Let me just see how I can forward this. Yeah, so maybe some of you have heard about this great success of artificial intelligence solving the folding of proteins. That was a big success that this Google company Alpha, this Google project AlphaFold was able to pull off. They were able, as the first, actually, many people had tried before. They had these continual challenges. There was like a data set of proteins, and basically their 3D structure and their sequence. So you can nowadays find the sequence of how the amino acids are arranged in proteins with modern technology quite easily. The question is how, when you have the sequence, do these strings of amino acids fold up to make the three-dimensional shape of the protein, which ultimately defines its function? And it was impossible until basically this DeepMind company or Google was able to really make this happen. And what they had done is they had, of course, developed a very elaborate scheme of treating the data using artificial neural networks and all the artificial intelligence tools they were able to throw at this. But it would not have been possible without having data, right? So they needed, of course, input from, they need to have the input of the sequences of the proteins, but also how these would fold up. And for that, you need experimental data. And this experimental data, that is basically now what we would call the encyclopedia or the dictionary, or the lookup table, if you want, of data that was available to this. And that was given to them by the protein data bank. You see here at the bottom, you can see the protein data bank. It actually has a few different names, but they all somehow share a lot of their data. And then the sequences, they came from another data bank, which is called the Big Fantastic Data Bank. So without this data, they would not have been able to actually make this prediction of the 3D structure of proteins. And the data basically had been around already for decades. So people had been collecting this data for many, many years beforehand, before they knew there would ever be somebody who would be able to use that data, for example, in this context of predicting the folding of the proteins from their sequence. So this is actually the motivation for, at least from my perspective, for why do we do this? Why do we collect data? Why do we want to make it available for the future generations of scientists? Because they may do something with this very different and much more elaborate than we can ever think of at the current point in time. So just to show you, I mean, this data, this is now the statistics of the data that has been basically uploaded to this particular protein data bank. No worries, I'm not in this field of proteins, but I just find this is a very good example. But you can see already since the 1970s, people have started to generate data and upload them on the scale of, you can see the top here is 20,000. On this scale, no, sorry, it's 200,000. This doesn't seem to be anything at all, but the numbers have been growing since. But hadn't they started already to do this back then, there wouldn't have been a habit established of collecting data in a data bank like this. And this data bank would not have the size that it has now, and it would not have been as useful for doing, for example, this artificial intelligence learning. You can see it's been growing basically exponentially. This later trend here doesn't seem to be exponential anymore. It's a bit linear. This has to do with a change basically in focus or technique. You can see here, traditionally, these structures have been determined by X-rays. So there has been a linear increase in the number of structures being reported and uploaded basically for a very long time, but it has actually decreased recently. And that is because there are other techniques like this one here, especially electron microscopy, which has really this exponential growth here. And the year 2022 is not over yet, so it's expected that this will really increase also much beyond this, so that this exponential growth actually continues probably. So that is, of course, sometimes what also happens, but the database, and that is also an interesting aspect, the database is basically immune to this change in technique, or really it's a totally different instrument. You don't go to a synchrotron, but you now have a lab installed instrument. It doesn't use X-rays, but electrons, but it was somehow still possible to still present the data in a manner that is normalized, like we would call it. So it is independent of the way that the data was acquired. And I think that is a very important aspect of such encyclopedias or dictionaries, that you can really compare information between different techniques. So it doesn't matter how exactly you did it, as long as you document your entry well enough so that it can be basically put in the same basis with other entries in the encyclopedia. Right. So when we think of what should a materials encyclopedia, so we now leave the field of proteins. I didn't want to go there anyway. We're now talking about material science, but I just thought this is a much better example than I could find anywhere in material science, at least from my limited perspective. But what if we were to now think about an encyclopedia for material science? What would we wish it would have? Of course, we want to have the same basis. Of course, the elements and the atoms are, of course, very important. So that's definitely something. But of course, a material is much more than this. So, you know, we think about phase diagrams, basically how do different phases of materials form and dissolve when we change the conditions like temperature and pressure and so on. Which crystal structures form, what symmetries do they have, what is the electronic structure, so the band structure of these materials. And since you're here, you've probably heard about the NOMAD encyclopedia, for example, where a lot of that is, of course, the topic. But other things like electrical, electron-optical, optical-mechanical properties, and so on, transport properties, a lot of these are also very important materials properties that we're definitely interested in. And that is just the bulk materials. So materials, then they can be structured, they can be nanostructures, so they have surfaces. And these surfaces can reconstruct. We can have topological states, like, for example, in topological insulators and so on. So there's a lot of materials properties that we would like to somehow cover in an encyclopedia about materials. And of course, then what if they come into contact with other materials that can then be now anything, right? So you can have wetting, you can have different contact angles, different surface and interface energies, and so on. You can have chemical reactions with other materials. So all this knowledge that we think we have about our particular system that we're interested in should now be captured in a way that is also somehow on the same basis as that of other groups that work on different materials and have their own very specific knowledge. Right, and then of course you can go even further when you go to nanostructures. They have very special mechanical and possibly also optical properties. Just thinking about surface plasma resonances and so on. So there are many of these effects which we would like to capture when we talk about materials, and that we would also like to make available as knowledge to the scientific community, of course. So that is what we would expect. But you know, when we talk about materials, we don't know everything about them often, right? So we have, we know something about how we process them. This is, you know, the famous materials tetrahedron. We know how we process them. We can learn something about the structure, or we do some computation of the structure. And then they do perform for some property that we designed them for, or for some purpose that we designed them for. And they have, of course, certain properties that don't only include the ones that we're after. And we applied characterization tools which give us an imperfect view of all these things. So the processing, we're not completely sure of exactly what happens. We, of course, try to keep notes of basically the temperature and so on, but what exactly happens there, sometimes you only reconstruct after we somehow build a picture of what actually happened during the processing. And the same is also true for the structure. We may have an idea, but only after we tested it, we find out what exactly it is. And it's not always, of course, a single crystal. I mean, often materials are polycrystalline, if they're crystalline at all. So yeah, so these ideal properties that we think they should be contained in a database that we design materials from, well, we don't always have them. We often have limited accuracy, for example, in data that we can derive theoretically, for example, by density functional theory or excited state calculations, or also MD calculations or whatever, or maybe even more coarse-grained theories. And also from the experiment, we always have imperfect experimental data from samples that we don't perfectly know everything about. And often also our measurements are only indirectly related to the properties that we actually would like to have in our encyclopedia here, for example, right? So, for example, the structure, let's say even the crystal structure, when we want to retrieve the crystal structure of a single crystal, it seems a simple thing, but there is, when you do a collected diffraction pattern, there is a problem of relating this diffraction pattern to a unique crystal structure. You need to have some additional computational algorithm. And for example, if you use direct methods, you get some probability. It could be this structure or it could be a different one. So often we don't have direct links between our experimental data and the properties that we're actually after. And that is, of course, the challenge when building an encyclopedia about materials that we're faced with. So we have not perfect eyes, neither in theory nor in the experiment, to actually observe what we would like to actually write into this entry for a certain material. There are a number of materials databases that exist. The ones that I can find, the ones that have the most entries are theoretical ones, because there it is the easiest to actually just produce a new crystal structure or test a new structure and calculate for it different properties. Here is, for example, what I could find about this AFlow database or encyclopedia or whatever you want to call it, of materials. There are different things you can do here. You can, for example, search for materials by entering the chemical components that it should contain, and different tools you can apply to the entries in this database. But I just wanted to also highlight these numbers here. For example, it has, of course, a number of different entries. For example, here 3.5 million enthalpies of formation, and you have then thermal properties for a fraction of these only, also band structures only a fraction of these, and so on and so on. So you have already a lot of materials in this theoretical database, but of course it only gives you a small fraction of the properties that we're actually after. So you won't find, for example, for these many materials that in principle exist, you don't have all the properties for all these materials, because it's not so easy to calculate them, let alone record experimental data of these materials, especially if they're maybe not very stable to make. And then as soon as you reduce increase the number of constituents in the structure, increase the number of different chemical elements, also the number of entries in the database reduces, even though the number of potential materials is much larger, right? So it's really also very costly to calculate all these different properties. Here's a different project that you may have heard about. It's the materials project that is run in the US. A similar undertaking where also basically one code calculates is used to calculate these different structures in a high throughput manner, so that really a very large number of different materials is being generated in the computer and then relaxed, and the band structures calculated from it, phonon band structures are calculated from it, and so on. So And also this has a number of tools. For example, you can see here, you can retrieve thermodynamic stability, electronic structure, phonon dispersion curves, and you can simulate diffraction patterns, and so on and so on. So you can, many of these theoretical databases try to produce as much as possible of information that could relate to experiment. And here is also NOMAD, which I probably in this context don't need to say very much about, especially since Laurie will also give a presentation afterwards on the encyclopedia of the NOMAD, the Novel Materials Discovery Laboratory. So I won't go into it, just to say it contains really a very large number of calculations, more than 100 million calculations. So this is really the largest database. Also because it incorporates data that is also contained in other databases. But I'm expecting to hear more about this by Laurie afterwards. Here's another one, that's another theoretical database. That's the Open Quantum Materials database, which then also tries to make the connection to phase diagrams. So basically having different crystallographic phases as a function of composition, and how these the boundaries between these phases are defined between different existing compositions. It is yet another database that's very interesting, contains a large number of materials as well. And all these databases, or encyclopedias, if you like to call them that way, also have, here it's actually explicitly mentioned again, have APIs where you can interact with them, you can extract your data, you can write your own code that automatically extracts data from this encyclopedia. So this is really the way that normal modern interaction with such tools should actually be, that your code can directly pull data from it and use that data without you having to actually browse through a book like in the old days. You had to look under the first letter, look up, okay, this is the structure, and you write down or copy the numbers. No, all these things can be crawled through automatically by code that you write yourself, if you like. Just to show you, here's something that's in the connection with the previous tool that I showed you. This is the materials similarity network, where really you can have different materials here, all these different nodes, they correspond to different unique materials. Here, this one, that's the lithium osmium oxide, just taken from this paper here about this tool. And you then have links between these different materials that define then, for example, coexistence relationships, thermodynamic coexistence or chemical similarity and so on, so that you can really follow these lines and find materials that are related to it, and they're also clustered by similarity. So this is also a way to visualize the different types of materials that you have available, and that is another aspect of encyclopedias. You want to have some visualization of the content that goes beyond just looking at your single page, but because we have everything available digital nowadays, it is possible and also necessary, because of the vast number of entries in these encyclopedias, that we get somehow an overview picture, that we can zoom out and somehow get an overview and get an impression of, well, the big picture and how things actually connect together. And this is one of, for example, the ways that can be very helpful for that. Now, coming to experiments, of course, there are also materials databases already that contain experimental data. Here is or hybrid databases. This one, maybe you're familiar with already or heard about. It's the CalFAT tool or database, or there's actually a whole community about this CalFAT principle. That CalFAT stands for calculation of phase diagrams. So these are phase diagrams that are computed, but to a large degree based on experimental data. So it's a way of interpolating between known data points by basically drawing these lines of coexistence here based on solving a system of equations. So by minimizing the Gibbs free energy of the system, assuming that the system really obeys this equation, where the Gibbs free energy is basically a sum of different energy terms that are now scaled with coefficients, and these coefficients are fitted to the known data points that you have. And these known data points, they can come from materials databases about containing experimental data, but also to some degree they're basically augmented by entries that are calculated. So you can have now these different contributions, and they each scale with a parameter that is fitted. But this actually works quite well. So this CalFAT community can really predict the stability of different phases in regimes that have not been measured before, which is what you really want to use, or want to do at the end. You want to use these encyclopedias to predict, for example, new materials, or to predict properties that have not been measured. And that is why we do this. It's not meant to be sitting in the shelf and not doing anything, but this knowledge wants to be used and should be used to really create new insight into materials and lead to the design of new materials with specifically designed properties. So this is the CalFAT community. I just wanted to mention a few to give you an impression. There is already a lot out there. And oops. Okay, here, but what does all these databases that I've shown you so far, they try to really describe quite a few properties of materials, but they don't come close to really being comprehensive in their description of materials. So here is just from a paper by Deegan. Actually, it's a quite recent paper from this year. If you consider this tetrahedron of material science, where what I've already explained, you have the process and the performance, the materials properties, and the structure, and that is all related with each other, and you have some pair of eyes on this, and that is your characterization tool. If you just consider not a simple material, let's say silicon, but a more complex material, for example, nanoparticle polymer composite that you want to design to have specific electrically insulating properties, if you want to use it for coating, for example, then of course, it becomes very complex. You don't find that in any of the databases that I mentioned before. This is now a composite material, and the properties of this material depend on the combination of different materials. So ultimately, that is what one would also expect from an encyclopedia, that you have the ability to combine different materials together and find out what comes out of it, or at least have tools that allow you to somehow make the prediction. But what do you need, like from an experimental point of view, what do you need to describe such a material, right? You need to synthesize your nanoparticles, and you somehow need to get them on the surface of your polymer. That means you have some solution mixing process going on. And then you want to characterize this, so you need to somehow slice it and make some thin slices of it that you can do, for example, microscopy on it. Then regarding the structure, it's not just the crystal structure, right? But you also need to now say something about, for example, how much of the volume fraction of the material is nanoparticles and how much is polymer. How are they attached to each other? And these are often terms that we still need to come up with to have a general description of these phenomena. But all this is, of course, part of many material science labs' daily work, right? So if we design an encyclopedia to describe material science, it should be actually our goal to be able to also describe these kinds of scenarios. And then, of course, you have properties of this composite now. For example, you have the dielectric constant or dielectric function as a function of frequency. You have some dielectric breakdown strength and so on. So these are some electrical properties, but also physical properties, for example, viscosity and melting temperature and so on. Then you have the performance in terms of the purpose that you've designed this material for. And then you have these different characterization techniques that you can apply that, like I told you before, deliver indirect data about what you want to find out, right? You want to, for example, quantify these properties. You only have indirect measurements of this often. For example, even an electrical measurement, you have some contact resistance that you need to characterize and so on. You can see it gets very complicated, and that is really the challenge that we're facing now. Really creating an encyclopedia that can cover and describe all these different aspects is really very challenging. Just to give you a few more databases where you can look up properties like this. For example, I just choose two, and there are many of these databases that are often very specific. For example, there is one about dielectric constants. Here's one that is about electron energy loss spectra. It's more related to the field that I work in. This one here is, for example, about crystal structures, which is interesting because the question is, how reproducible is the data in these databases, right? So if you, that is another aspect that you need to ask yourself when building encyclopedia. What basis do you describe your data in? What metadata do you use to describe your data in order to make it reproducible, right? The left database just gives you raw experimental data. And for example, you can in principle extract a dielectric function from data like this. However, you need to know more about the sample, for example, that has been investigated. For example, is the surface really clean? Is there maybe an oxide that grew on this? Well, maybe not in copper oxide, but for example, if you have silicon, I will show an example, and these things. On the other hand, this database on the right-hand side, here really, yes, there is experimental data, for example, diffraction patterns and so on, but then it also contains this normalized representation, I want to call it, because that is something that can be compared with other databases and other representations of materials, and that is the crystal structure, because from this crystal structure, you can do a lot. You can do a calculation, for example, of the band structure. You can calculate, again, a diffraction pattern, or if you really do an excited state calculation, you could even calculate yield spectra like you have on the left-hand side. So if this crystal structure was correctly extracted from the experimental data, that of course will always be a good representation of this entry in an encyclopedia. Right, but just to show you these instruments, and my background is electron microscopy, so I squeeze in sometimes just a few examples from this field. So I hope you forgive me for not being super general here, but I have to use something to really show what I'm talking about. But from a single instrument, in this case, an electron microscope, you can get a very wide range of data, right? And this is true also for other instruments. You can drive them often in a few different ways, or you can even use them in non-conventional ways to really create data that you're really after. How do you describe all that, right? So how do you have a general description of this type of experimental setup and the data that it can deliver that both is truthful to the experiment that you are collecting, that means describes it very well, but also can be then related to experimental data or theoretical data by other groups and so on, right? So this, I won't go into detail what all this is. I'm just wanting to give you an impression. Just a single experimental setup can often deliver quite diverse experimental data. And it comes worse. Here, this is just as an example, this is the physics department here at Humboldt Universität. And next to it is the Iris Adlershof, actually where the headquarters of FAIRmat are actually located in. And you can see now there in these two buildings already are a number of electron microscopes that are installed there. And each one of these is like very different in their capabilities and what it can deliver. So now you have a lab with not just one instrument, but you have in this case maybe 12 instruments, and the data becomes even more diverse. And that is just one technique. It's electron microscopy that you would describe as one basically technique name in your encyclopedia, yet in itself, it's already quite diverse. And now if you consider including also more different techniques, not just electron beam techniques, but let's say X-rays and atom probe and scanning probe microscopy, but all the electrical transport, optical spectroscopy. I mean, there's such a wide range of techniques that to describe this all is actually quite complicated. And this is actually the challenge that the FAIRmat project is facing and trying to pursue and trying to really at least make some progress in. So now I want to come to different requirements that I already hinted at this a bit, but I wanted to really write down now individual bullet points of what are requirements that I believe are very, very important for such experimental encyclopedias or databases. First, like I think I already mentioned this in the few examples that I showed. The data must be described by metadata that is somehow standardized. That means we need to have a common basis or common language. Right now, I'm speaking English to you and not some other language, because that is how we can understand each other. And the same is true also for the metadata that describes our experiments. So we need to really make sure that this metadata is so-called normalized. That means when I say energy, then you understand what I mean by energy. And when I say something about, for example, unit cell, then you know exactly what that means. And microstructure, it's even more complicated, and so on. So the simple words, I think we can all agree on, but it's quite amazing how diverse opinions can be about something. For example, the differentiation between sample and specimen, right? There can be long debates, what is what, and one needs to define this and really make sure that if I say, use this word, then that is actually what it means, and so on. So this should also then include self-consistency checks, so that really it's being checked that the data that is being inserted in such an encyclopedia is also self-consistent and does not contradict itself. The data should then, and actually this is what's already implied a bit by the first point, it should be linkable then also between different techniques. And that is important when, for example, you want to compare. We have an example that we're currently working on, for example, comparing band structure information obtained by ARPIS, that means angular resolved photoelectron spectroscopy, and electron energy loss spectroscopy. So these are very different techniques. One uses photons, the other uses photons and electrons, and the other one uses only electrons. They produce very different data, but you somehow must be able to link these data together. And this point of normalization actually is a very important one. Then the data quality should be verifiable, right? So if somebody uploads data, then it should be somehow verifiable that this data is actually useful. Okay, I hope you can still hear me. Okay. Somehow the connection was lost here for a second. Can you still hear me?
Yes.
Okay, good, excellent. Good, I continue then. Of course, a small database that only contains 100 or 200 spectra is not very useful because you won't find what you're actually after in that. So really often these databases get ignored if they don't reach some critical mass like a significant number of uploads has been ingested. And this cannot be done by a single lab, but it must be a joint effort of many different labs. And this joint effort can also not be, it cannot be commanded. So I cannot go to my friend in the lab next door and say, okay, all the data that you collect the next year, you have to upload. Well, it won't work that way because, yeah, it just doesn't. So we should actually create incentives for people to really work with the system and upload their data voluntarily. I mean, all of us have a smartphone in our pocket probably or somewhere because it's so useful, because we find it's really something that we need. And the same should be then also true for the use of these databases, so that we create them in such a way that people realize, or scientists realize, this is something I need. I really want to upload my data to it because I get added value from it. I benefit from it. So, and then, of course, the aim should be to connect really as much related information as possible. And this is already in principle what I said, it must be community effort, right? And ingesting data from similar databases is not a crime, right? As long as you keep reference to the original database, actually everybody benefits from this. If I can search your data on my database and you can search my data on your database, both of us have more data and have more to compare with. This is actually a good thing. Right, and there should really be an interface also for having tools that can crawl my database. So typically this is done using a REST API. This can be basically, these are commands that are sent via internet commands. And there should also then be role model examples, how such database can be used. I started with one right in the beginning about the protein folding one. I think that is a very good example. One can show that really was a success. And for me, at least, this is a motivation of really pursuing such database activities also in fields that have not been explored yet, like the material science field that I'm currently talking about. Let me just somehow support this, everything that I now listed here, with a few examples, and then I will be done. So what I said about metadata must be standardized, it must be normalized, and linkable between different techniques. So I want to just point you out, there are already activities like this, and I know these are just two that I will mention that are local here, and others exist also. But FAIRmat, this consortium, this NFDI consortium, FAIRmat, is already working on a few experimental techniques to really somehow find a good way to describe these metadata and really come to a unique, basically, set of descriptors or keywords that describe the metadata that is collected. And of course, along with that then comes the development of converters that convert then between different data formats into basically this common data format. In this case, the idea was to really use something that was already established, Nexus, which is a format that is used a lot at synchrotrons and neutron scattering facilities and so on, and somehow use all the development and design of basic metadata keywords, and then of course expand it and extend it, but use the same principles of how Nexus was designed for synchrotron experiments, also for these other techniques. And then also at the Helmholtz Center here in Berlin, there is the Helmholtz Metadata Collaboration Platform, which meets regularly to really discuss also, yeah, what does it mean? For example, I mentioned before the example of specimen and sample. So what actually means specimen? What means sample? Can we write down a description that we all agree on, where we can really distinguish between the two, and so on? So these activities take a lot of effort and time, and but somebody needs to carry them out so that the whole community benefits from this. And I'm very happy that this can be done within FAIRmat and also within Helmholtz, right? But then metadata must also be, once you create metadata, you need to also visualize it and make sure that you can really see what you've created there. And here, Shajir Shabi has really developed this 3D viewer for metadata. So this is like a metadata tree, like this Nexus metadata tree, and you can really then look, okay, what are now derived keywords that are derived from, for example, in this case, NX process that is used to process data, what program is used to process the data, and so on. So the metadata that describes your data should also be visualized so that you can really see what you have there and not just have long file that you cannot read all the way to the end. So you can really, like I've shown you before, this interaction between different materials. The same is also now true for metadata. You need to somehow see how do these metadata tree structures look like when you want to get an overview of them. Right, and the next point, data quality should be verifiable, right? I just want to give you one example, and I know this is again specific to the field that I work in, but this is now an electron energy loss spectrum of silicon, where there is some band structure information hidden in this. So, so the band gap is in this regime here. There's a direct and an indirect band gap. And they're between 1 and 3 eV. So the direct band gap is at 3.3 eV and the indirect one at 1.1 eV. You would be able to extract that from the raw data, which is this green curve here, but you have to do some processing of this data to really remove some relativistic effects and so on. I don't want to bore you with this, but you can then compare it. And that is what I mean by normalizing data. You want to bring the data into a format that it can be compared with other data, in this case, optical spectroscopy. So these dashed curves here are optical spectroscopy data. And here is basically the dielectric function extracted from the EELS experiment. And you see, they don't agree very well. You can see, yeah, the band gap kind of comes out right, the direct and the indirect band gap, but the dielectric function itself, yeah, you would say, okay, that's sort of a good agreement, but not very good. But if you, this only, now this is a different representation. This is now with the real and imaginary part of the dielectric function. You can see the disagreement is even worse than if you have this N and K representation. But if you now know something about your sample, and that is really information that one needs to really invest in recovering, silicon grows a native oxide if you expose it to air. But if you then assume that there's also a silicon dioxide silicon interaction, and you can then include that in reconstructing this dielectric function from your experimental data, then the agreement between the EELS-derived dielectric function and the optical dielectric function gets much better. So that is what I'm saying. Often we don't know everything about the sample that we collect our experimental data from. We should know a lot more, but our techniques are limited. And we really, then if we want to make data reliable, we should really then also invest into this normalization of data. And that is often a reality check, where we then find, it's probably not what I thought it was. So I have to work harder to really make this a good entry to the database, because otherwise, if I deliver this dielectric function here to the database, to my encyclopedia, and say, oh, this is the dielectric function of silicon, it would actually be almost more harm to put this data in than to not have any data, because it might be taken as grounded truth by others who then use it for whatever purpose. So we often also have a responsibility for our data that we upload, but this shouldn't be offloaded to the individual scientist, but the encyclopedia itself should contain these checks and balances internally to make sure that scientists have the tools at hand to verify whether their data actually is good or not. Yeah, I will skip ahead a bit here. Oops, that's the way. Okay. But then just this last point I wanted to make, and that goes quite quickly now. It's just a short video I wanted to show, but I think that is very important because it really, yeah, it's at the core of what we invest a lot into when really building this encyclopedia also for the FAIRmat project, because in order to get enough data sets in there, I mentioned this before, one has to really convince the community to work with it and to provide tools that really make it attractive to them. So this is basically how Nomad has this model that you upload to a repository and you put it into an archive, and then you can also then of course bring that into the encyclopedia, where then the public can look up the data. But in order to really attract groups to really work with the system, you should provide tools. For example, here is this artificial intelligence toolkit, and there has been a tutorial on that already. Here is now a short video of, this is the database. When you upload to it, you can create a new entry in it and you upload your data. It should be very easy to use, so just drag and drop and so on. But you should then also be able to interact with your data. So there should be software like this, software that now runs on the server, processes the data. You can now do different calculations of it. Everything that you can do on your desktop computer, for example, with your data, you should be then also be able to do online and more. The idea is to really have unique tools available. And this, for example, now includes also a graphical user interface where you can work directly on the server, on this database server with your data and interact with it, and also write scripts that extract information from it, and so on. I won't go into detail what all this means, just to show you this is what we started to actually now do, that we have interactive processes or tools on the database server itself, so that the data is already on there, and then you produce more data that you derive from it just by working with it, and you can then also visualize the data there. I won't go into detail what all this means because this is specific to the techniques that we work with, but just to show you, you can really visualize one-dimensional, two-dimensional, four-dimensional data, and you can also then run Jupyter notebooks, for example, to really process data in a way that you might not have available in your own lab, or where, for example, the computational resources of your laptop or whatever you have sitting on your desktop don't suffice to do the processing. In this case, for example, it's a reconstruction of a four-dimensional data set acquired in a TEM in terms of typography. So this is really an iterative process that can take several hours, even on a good computer. So having really this offloaded to a central server where the computational resources can be provided more easily because centralized, this is really a benefit. And then you can visualize the results that are already saved then within this data format that you loaded your data, that you use to upload your data, and you can really look at the reconstruction. And in this case, you can now see really the atomic structure that was reconstructed from this data set. And it did not make any sense to look at the original raw data without having applied such a reconstruction, because it's not humanly interpretable. You need the computer to really do this. Anyway, I think I was able to show you that these points that I've listed here, they really apply a lot. And of course, that the last point I want to make now is that you have, of course, role model experiments, of course, but also there needs to be really a new philosophy behind the development of these databases. And that is a picture from a paper that I've already showed one or two slides from before by Deegan from this year. They find when you build such digital infrastructure, like an encyclopedia for materials, actually there is, they call it a digital twin. So a lot of the principles that are already well known and established in experimental material science, where you really want to learn something about a material, they also apply, or they can be translated to corresponding principles in basically the building of a digital infrastructure. Of course, there is no processing of a material, but there are methods and workflows that you apply in a digital way. You don't do any characterization by looking at your material, but you evaluate entries in your database and so on. And they have now a very nice correspondence here. This is basically what we know already from material science, these different aspects of how we describe and research in materials, but also in an information science point of view, these really find the correspondence. For example, the processing step used to process or to synthesize materials translates to this procedure of acquiring, integrating, and analyzing digitized information, and so on. Of course, you want to then at the end also have tools that you want to run on different entries in your encyclopedia, and of course these need to be these need to be efficient, and they need to actually get to the point that you really want to make at the end. So the efficacy needs to be high, which translates to the performance that you want to have, for example, for the real material that you've designed, and so on. And if the sustainability, for example, of a material translates to the FAIR principles, right? Can what you do and what you uploaded to your encyclopedia and the digital infrastructure that you built, can this also be reused in the future? And then we can now draw the full circle back to do something completely new. For example, predict the protein folding from the data that you upload now, or something totally different, of course, because it may not be proteins, but something that you would not have envisioned when you really created the database. So my summary slide just tries to collect the different points that I've tried to make. Ideal materials encyclopedia, really, of course, encyclopedia stands for the complete knowledge. We may probably take a few years to really get to that point, but this is really, in principle, the goal, and we should at least not build structures that would prevent this. So we should keep this ideal goal in mind, even though we may not reach it next week. And then, of course, I listed already a number of theoretical materials databases. They are quite advanced when we compare them to experimental databases, but this is really actually the state where we really ultimately want to be at. Having this really large number of entries and also this this very good connectivity between entries in there, that you can really compare one entry with all the others, which is a challenge in experimental material science, because the techniques are quite different. Right, and that is really the point, the next point here, that really making these links is a challenge. But if we can normalize the data to some fundamental properties, there is hope that this connection can be made. And it's very important that really the data quality is checked. And now also in theoretical databases, there are these things. For example, one needs to make sure data is converged. The same applies, of course, to experimental data. It must be somehow self-consistent. And you all are needed in this. So there cannot be one lab by itself doing this, but it really has to be a community effort. Thank you very much for your attention.
Yeah, so thanks a lot, Christoph. I guess if there's now any questions, we could take them in. So maybe Christoph directly answer if somebody, maybe you can raise your hand in Zoom, so that Christoph will know that you wanna ask something. Okay, there's also now questions in the chat, so you can also pick some from there.
Yeah, I see a question in the chat. I can read it, I guess. And the question is there inclusion of experimental data in NOMAD on the horizon? And the answer has already been written. Yes, indeed it is. So actually what I've just shown you was indeed this short video that I showed you was already experimental data in the NOMAD database. There's more, I guess, you, Laurie, will say more about it potentially, I'm not sure. But
yeah, I will mostly talk about theoretical data, but yes,
okay.
There is of course now lots more of the experimental data. For example, the EELS data that you mentioned is already in, and also other examples.
Yeah, and it's also possible to really have a local installation of this repository on your, of the NOMAD repository, which ultimately then you can upload data to the encyclopedia with. It's true, the NOMAD encyclopedia at the moment, as far as I know, the actual encyclopedia, the publicly available one, contains so far mostly theory data, but yes, it's really in the process. Yeah. I see another question by Hampus Nastrom.
Yeah, hi, Christoph. Thanks. I really liked the slide with the requirements. I thought that was very nice. So, in your opinion, what do you think about these? Now we move from theoretical to experimental, right? And you say this, we need a self-consistency check to say, okay, we've determined the band gap. How do we know that this is really the band gap of the material? But I think it's like a continuum, right? At some point, we need to say that we trust a certain level of certainty, and we need to put that. And how do we determine? How do we really quantify this trust in a material, in a property? Because and also, like, is the material still the same after we measured it, and what has changed, and so on? It becomes very sort of a question of trust, right?
That is true. And I think that has been discussed many times, and people have proposed things like a point system. Like, for example, when there's a paper that has been not downloaded, but has been cited 1,000 times, it probably contains some very important truth. And the same might be true also for data that is uploaded to encyclopedia, that if this is used many times by others who don't find a problem with it, maybe it's more correct than data that has not been used by anyone. Well, that is maybe not a good point, because if it's not used by anyone, it's just nobody found it. But, I think it's this really, there will be credit that probably will have to establish over time. Yeah, I guess the use of this data must also keep in mind that there's a slight chance it might not be correct. So this is always something that any analysis that uses data from a database has to somehow build into the analysis algorithm. I guess that's the only way we will be able to deal with this in future. That is how scientific discovery happens, right? Sometimes we find out, well, we don't have any particles that go faster than the speed of light. It was just a loose plug somewhere, right? Like they've had happening when there was a particle experiment that was predicting this. But at the end, they found out it was just a fault in the experiment. Sometimes you can do very careful experiments and still make a mistake, or some process gets in a way that you were not aware of, maybe a new phenomenon and so on, right? It's never possible to have a complete...
Yeah, no, I agree. And I think that usually in the mass, you will see the outliers if you have enough data points. I mean, this is what happens. So the Perovskite database that is now on the Nomad as well with the data, there you can very clearly see that when someone has input, say, a short circuit current per solar cell, which is above the theoretical limit, you very clearly see that this is not a correct data point, because all the other data points are following a curve, and then you can very clearly see it. So that's also, I guess, an option to trust more, and then just by the outlying effect, see sort of what is. Yeah.
Exactly. And potentially invest more into this particular outlier because it might be correct, right? But then you should really have more investment into it and not just give confidence for free. Yeah. Okay, there's a comment here referring to the establishing a FAIR metadata standards, like with the Helmholtz metadata collaboration. And the next, okay, so there's a question about the Helmholtz metadata collaboration and also the Nexus format that was now proposed already by the FAIRmat consortium. Yes, these actually the same people are in both groups and talking to each other. And ideally, I mean, what the Helmholtz metadata collaboration is trying to build, it's not a data format, but it's defining words and defining expressions that are used in the description of data. So metadata keywords, if you like. And the idea is that really the definitions that are created there will then be actually the definitions that are also used for the metadata format. So these are actually, to some degree, synergistic, not totally, they're not really in competition to each other. Yeah. But I do have to say, like, Berlin is not the only place in the world, so other places also have similar and comparable activities. And there is probably some work that needs to be reconciled and that is running in parallel right now. And I know of a few examples. I don't want to list them now, but there needs to be, of course, communication. Communication is really very important. And that's also one of the reasons why we have these tutorials right now, that we talk to each other and also find out what others are doing. Just by getting our word out, we will get a response probably. And hopefully this will then strengthen the communication. I see no further questions, so thank you all.